let's say we have a system. The system looks like this. One, two, three, 4, and 5. And we want to figure out the min path set for this particular system. So what we're going to do is we're going to say, all right, what are all the paths that if you cut them, the system will not work? So notationally, it looks like this. For the min path, we have x such that for the structure function equal to 1, and for all y less than x. So y is going to be 0 if x is 1. That the structure function for y is equal to 0. The value is equal to 0. So if we take away the min path, then we're going to have the system not working. This gives us an upper bound on the system reliability. Now, why do we care about an upper bound? Well, because sometimes if we have something like this, it's fairly simple to calculate the exact reliability, where you just take the structure function and plug in the probabilities. But if we have a big complex system like you will in the case study, it doesn't work quite so well. So it's harder to do more in algebra. So anyway, so for this case, our minimum cuts, well, we're going to have 1 and 5. We cut that length, the system won't work. We're going to have 2, 3, and 4. I'm sorry, minimum paths. These are all minimum paths, not cuts. Okay, so if you have only 1 and 5, the system will work. If you have only 2, 3, and 4, it'll work. If you have only 1, 3, and 4, it'll work. It'll work. And if you have only 2 and 5, it will work. So the way to represent these, that we can go back and make it easier to calculate the function, the structure function for the reliability, is to model them as being in parallel. So now we're going to say this can be modeled like this. And I mentioned this a little bit on Monday. We're going to have 1 and 5, 2, 3, 4, 1, 3, 4, 2, and 5. So the structure function for this, now we have, since we're in parallel, 1 minus, and then each one of these pieces. So 1 minus x1, x5, 1 minus x2, x3, x4, and so on. And then we can plug in our probabilities, enter them if we know them, and calculate an upper bound on our reliability. So min paths, that modeling system gives us an upper bound. Now we're going to look at min cut. So in the min cut system, now we're saying, okay, what are the sets of components that if we cut them, the system will not work? So in this case, if you were to cut 1 and 2, nothing's getting through. If you cut 3 and 5 or 4 and 5, nothing is going to get through. So notationally, we represent a min cut as x such that the vector x such that the structure function gives you a 0 and structure function of y, another vector gives you 1 for all y that are greater than x. So anything beyond that includes more than the min cut set will make it work. But if it's this min cut set, if this vector is such that the min cut set is cut, the system is not going to work. This gives us a lower bound on the system reliability. So in this case, the min cut sets, we have 1 and 2, 3 and 5, and 4 and 5. And all 3 of these have to be working. So what does that sound like? Well, it sounds like series. So now, to get the lower bound on the reliability, we're going to use the min cuts. model them like this, as if we have 1, 2, 3, 4, 5, 6. So now we're going to use this model to get our structure function. So we're going to say, all right, they're in series, so this guy is just going to be 1 minus x1, 1 minus x2. That times, same thing for this guy, 1 minus x3, 1 minus x4. And you do the same thing for this last set, and then plug in your reliabilities, your p's here, and that will give you a lower bound on the system reliability.